Hello ma'am, I'm Shantanu Verma of BTech CSC 4th SEM and I'm here to represent my presentation on the topic that you gave, Decade Counter Asynchronous. Well, before starting that, let's understand what the counter is. A counter is a device that is used to count binary numbers. A counter is basically an application of flip-flop and it is constructed by cascading number of flip-flops together. The next point is the stages of the counter depends on the number of flip-flop. That is, n number of flip-flop can count up to 2 raised to the power n number of pulses. For example, if you have 3 flip-flops cascaded together, then the counter will have 2 raised to the power 3, that is equal to 8 different stages. Now moving ahead to asynchronous counter. Now first understand what an asynchronous counter means. A counter in which the external clock is only given to the first flip-flop and the succeeding flip-flop are connected by the output of preceding flip-flop. Well, that means, for example, if you have 3 flip-flops connected together or cascaded together, the input of the first flip-flop will be the external clock that you have given. The input of the second flip-flop will be the output of the first flip-flop, and the input of the third flip-flop will be the output of the second flip-flop, and this cycle goes on. Now, as the clock signal moves in a ripple manner like a wave, therefore it is also called as ripple counter. Now moving ahead to our next slide, that is the different types of asynchronous counter we have. Well, I have mentioned a few of them. Let's go. First, up counter. Second, down counter. Third, ripple up down counter. And the fourth one, that is my topic itself, ripple Bcd counter. Now before going to ripple Bcd counter, let's first understand what a Bcd counter is. A Bcd counter or binary coded decimal counter is a serial digital counter that counts 10 digits and it resets for every new clock input. As it can go through 10 unique combination of output, it is also called as decade counter. As I have mentioned how a Bcd counter counts. For example, the 0 is represented as a 4-bit 0000, 1 is represented as 4-bit 0001. Now next 2, 3, 4, 5 and it will go up to 9, and after that 9 it resets to its initial value, that is 0000. Now to make a ripple Bcd counter, we'll need a 4-bit binary counter that will act as a decade counter by skipping its 6 output. In 4-bit counter, it will have total 16 outputs, that is, it will start from 0 and L at 15, but to be a Bcd counter, it should eliminate its 6 outputs. Now, a ripple Bcd counter is same as ripple up counter. The only difference is when Bcd counter reaches to count 10, it resets its flip-flop. The output that I have shown is just like that. It starts from 0, 0, then 1, after that 2, 3, 4, 5, 6, 7, 8, 9, and as soon as 9 occurs, the next digit will be a 0, 0. That is, it comes in its reset position. I have shown a cycle that how a ripple Bcd counters do its work. First, it counts 0, 0 and the next one and the next digit will be 1, the next digit will be 2 and so on, 3, 4, 5, 6, 7, 8, and as soon as the 9 comes, the digit after 9 it resets it as 0. Now moving towards the construction of ripple Bcd counter. Well, it is made by using JK flip-flop, that is, we need 4 flip-flops cascaded together. And the output of the flip-flops are Q0, Q1, Q2, Q3 respectively. Here in flip-flop, PR stands for preset and CLR stands for clear. So in decade counter, we'll have to start from 0, but we have to stop at 9 and then again go back to 0. For this, we have to see the case when the counter counts its value as 10. As soon as 10 has arrived, that is 1010 mentioned in our graph, we'll have to reset our flip-flop. Now for reset and set action in the flip-flop, we have used two asynchronous output, that is preset and CLR, that is mentioned in our diagram and shown in our flip-flop. When clear is low and the output Q is 0, our situation comes to reset scenario. In the similar way, when our preset is 0, then our output Q will be equal to 1 and that will come in the set scenario. But we want the recent action. That is why we have connected preset to logic 1. Now, by connecting preset to logic 1, the effect of the preset on the flip-flop will no longer effective. And we want clear is equal to 0 because we have to go to our initial stage, that is 0 0 0 0 as soon as we encounter the digit 10. I have mentioned a table, that is when the digit 10 occurs, our output follows like Q3 will be 1, Q2 will be 0, Q1 will be 1 and Q0 will be 0. Now before reaching these outputs, I have to go my initial stage, that is 0 0 0 0. For this I have NAND gate. Yes, now NAND gate will be connected to our Q1 and Q3 output. Now here one question arises that why we don't have connected Q0. We don't need them because Q1 and Q3 are altogether high in the case of 10 only. Yes, 10 is the first case when Q1 and Q3 are simultaneously high. Now taking two high input, that is Q3 input and Q1 input in a NAND gate, result to be 0, and this result 0 is connected to all the clear input of all the JK flip-flops, and this is how we achieve the situation of making clear 0. Now output of our NAND gate is 0 when we have 10, and this output is connected to all the clear input of flip-flop as I've talked earlier, and this will reset our flip-flop. It is basically the working that how a BCD ripple counter works. I've made a table also that we can go through it. Yes, the states are given, the outputs of different flip-flops are also given, and the condition of the stage is also given where the flip-flop resets itself. Now I would like to end my topic with my last slide, that is advantages of asynchronous counter. The first is it can be easily designed by D or D flip-flop. The second, it can be used in low speed circuits. The third, it is used as divide by n counters. Well, that means dividing the input clock frequency by n. And the fourth one is they are also used as truncated counters.